Comet elliptical orbits are often considered one of the mysteries in cosmic phenomena. Halley's comet visits the solar system approximately every 76 years, and its orbit appears remarkably stable. However, according to Einstein's general theory of relativity, orbits due to gravity should gradually become unstable, leading to energy loss. Comet orbits do experience minor energy loss, example, due to mass evaporation, but it's so small that they can maintain their periods for thousands of years. But to fully explain this phenomenon, we need to delve deeper into Kepler's laws and the principles of natural balance. In this article, we'll connect comet motion to natural phenomena using the wave analogy and unravel the secrets of sustained cycles through the concept of field. Comet elliptical orbits and Kepler's laws. Comets orbit the Sun in elongated elliptical paths. At perihelion, closest to the Sun, their speed dramatically increases, while at aphelion, farthest, it slows down. This is explained by Johannes Kepler's second law, the law of equal areas. According to this law, the line connecting the comet and the Sun sweeps out equal areas in equal times. Therefore, in the narrow part of the orbit, perihelion, speed increases to maintain the area, and in the wide part, aphelion, it decreases. Take Halley's comet as an example. Recorded since 240 BC, its period varies between 74 to 80 years, but averages 76 years. General relativity explains orbits through the curvature of space due to gravity, but for extreme elliptical orbits like comets, Newton's law of universal gravitation and Kepler's laws are more intuitive. Relativity corrects subtle effects, like Mercury's perihelion precession, but for comets, planetary perturbations, example, Penguin's laws of Saturn and Saturn rotations. Relativity corrects subtle effects, like Mercury's perihelion precession, but for comets, planetary perturbations are more intuitive. Jupiter's gravitational influence, or non-gravitational effects, gas ejection, are the main causes of period variations. The instability, what I think, is indeed observed, but energy loss primarily appears as mass loss from the comet's ice evaporation. For instance, Halley's comet loses 1 to 3 meters of material from its nucleus surface per orbit, equating to about 0.1 to 0.5% mass loss. This changes the long-term orbit, but appears as precise. Returns in the short term. Similarity to natural phenomena, the wave analogy. To understand the principle of this elliptical orbit, we can use the analogy of ocean waves. A calm water surface, wide area, symbolizes the slow motion at a comet's aphelion. As a wave rises, the surface area decreases, accelerating the speed, in similar fashion to the comet's speed increase at perihelion. When the wave reaches its peak, the area can't shrink further, so energy disperses, returning to a calm surface. The reason this process repeats is the existence of the ocean as a field. The field maintains energy balance, enabling sustained cycles rather than one-off motions. For comets, the solar system's gravitational field plays the role of this calm surface. Kepler's second law can be seen as the field naturally adjusting speed through area changes. Without a field, motion would dissipate or become unstable immediately. For example, a rocket shuts down after fuel exhaustion post-launch, but comets cycle for billions of years thanks to the Sun's gravitational field. The role of the field: balance in micro and macro worlds. The field, what I think, is not mere space. Einstein interpreted gravity as the curvature of space, but this seems like only part of the field's variations. In the micro world, quantum fields or electromagnetic fields sustain motion. In the macro world, gravitational fields do. A comet's orbit arises from this field's balance, with harmonious energy distribution being key, rather than force-centered, universal gravitation. Human-made machines, airplanes, cars, ignore such fields. For example, cars inevitably shut down due to fuel consumption. But nature forms fields through spontaneous balance. Quantum computers also struggle with stable cycles due to noise and energy loss. In contrast, comets conserve energy via Kepler's laws within the solar system field. maintaining long-term cycles despite minor losses. In fact, Halley's comet loses about 3 tons of material per second, but this is a tiny fraction of its total mass, about 2.2 times 10 to the power of 14 kilograms, ensuring a lifespan of tens of thousands of years. Conclusion: nature's principles and human limitations. The elliptical orbit of comets isn't fully explained by general relativity alone. Kepler's law of equal areas serves as a complement. This suggests shifting from force-centered thinking to principles of balance and fields. Nature achieves sustained cycles through these principles, but human artificial creations find it hard to mimic. Future comet observations, example, Halley's return in 2061, could deepen our understanding of this mystery. Applying these principles could inspire designs for sustainable energy systems.